Morning, y'all. Doing okay this morning? Couple things. Don't forget we're having a quiz on Tuesday, so that's this coming Tuesday. It'll be at the end of class. It'll be a half hour, 15 questions, multiple choice, just like previously. All right, we'll have a time of review if you have questions. Well, today we can answer any questions if you have any. Any questions about the quiz? You're clear on what's on it? Do the homework. As you said, you recognize that there were some homework questions on the last quiz, right? They were basically the same, or very, very similar anyway. And then also sort of the notes and reading through the chapters helped too. The food drive, I don't think I gave a date for y'all, but the food drive officially ends on the 28th. But let's say that our due date, let me look at our calendar right quick. Let's say that our due date is well, let's say it's the 28th, okay? That'll be the 28th. We don't have class on the 26th. So we'll make our due date be the 28th. And remember, like I said last time, how many points did I say I give? Up to 200? Up to 20, I think, right? 5 points for every 50 items that bring in. So on average, that would be about 4 items per person, right? Because there are about 58 people. Yeah, I'll send. We have a couple weeks, so yeah, I'll send you an email. All right. They need cans of food items is okay, but really they need like personal items, you know, like non-food items, toilet paper. I don't know, you know, right? Soap, shampoo, stuff like that, because you can't buy those things with food stamps, and so the food banks are often deficient on those things. All right. A lot of people in Thibodeau need help, like they find themselves in bad situations because of health problems, or they lost a job or whatever, and you know, I think most of us have more than we really need, so it's a good opportunity to share with others. All right, and you get 20 points in the class. That's a pretty good deal too, right? All right. Sort of to recap from last time, we started on fluids and pressure. Several topics. There are a lot of sort of topics, and you know they're loosely related, but some of them might seem a little disjointed. Defining pressure. We define pressure. You should have this in your notes. I'm just sort of recapping it. Pressure is force per unit area. There's some homework problems where you're actually calculating pressure. Talked about the different units for pressure. Atmospheres is equal to 100,000 pascals, which is newtons per square meter. Boyle's law, which just says that pressure is proportional to 1 over V. That is, if V goes up, then pressure goes down, like in your tire, for example. Then also Pascal's principle, which is the principle behind hydraulic lifts, for example. And it just says that anytime you put in a pressure, that you feel that pressure throughout a fluid. And this is based on the incompressibility of fluids. Excuse me, not fluids, but liquids. That almost all liquids, I think all liquids, I can't think of one that's not incompressible, but like water, for example, is incompressible. Hydraulic fluids that you use in hydraulic systems are incompressible. Why don't we use water in hydraulic systems? If it's really cheap, right, and it's incompressible, so why not use water in a hydraulic system? You think of one big reason? Air bubbles? Are you guessing, or do you know the answer? That is the answer? I don't know. They cause lines to pop. Okay, because they're compressible, and they can be compressed down to a small shape, and then when they come back into something, they can decompress and get bigger, right? I was thinking more along the lines of rust, that if you put water in a hydraulic system, it'll rust. But maybe you're right, Kyle. Are you right? Okay, I was guessing. Okay, all right. So anyway, that's Pascal's principle. Pressure in is pressure out. We worked through a couple different examples. There are some homework problems too that are similar to that. And then pressure due to the weight of a fluid. Pressure is equal to rho times G times H plus, I'm going to write this as P atmosphere. You'll see this in your homework. I don't know that I wrote it explicitly like that, but if I'm at a certain depth here, I have this column of liquid that sits on top of me, and it creates this pressure, rho GH. But then in addition to that, I have the pressure of the atmosphere that's pushing down on top of me. So the total pressure here is equal to the sum of these two. All right. We watched that video about the straw, and we decided that for Welcome Back Day, our class is going to put on a straw competition, right, to see how far people can suck up water into a straw. Now, the general idea about this, just want to make sure that you're clear. If you have a drink and you have a straw in it, there is atmospheric pressure that's pushing down on the surface of your drink, and so that atmospheric pressure is also pushing up into the straw. But if the straw is just sitting there, you also have the atmospheric pressure that's pushing on the other end. So you have this equilibrium between the two pressures, and so nothing happens. But then you come along, and you put your mouth on the straw, and what you do is you decrease the pressure on the top side of the straw, and that causes the fluid to come up into the straw. So you put your mouth on this, my nose. Oh my goodness, that's a big straw. Anyway, you suck up and you make the pressure inside the straw here to be less than the atmospheric pressure, and then that causes the fluid to come up into the straw. Okay? Now, he gave a theoretical limit for how long a straw can be. Do y'all recall what that was roughly? It was about 10 meters, yeah. Now, what that means is, let me show you something else. So remember we also went over the manometer, where the manometer compares the level of fluid, and you have a certain pressure here, and then you have a certain pressure here. I'll call this P naught, and this is the pressure that you want to know. And in this case, the pressure on the right-hand side compares in what way to this pressure? Is it bigger, smaller, or the same? The pressure over there, your unknown pressure, is it bigger, smaller, or the same as this pressure? Manometer. It's the same because those two levels of the fluids are the same. But if on the right-hand side, if that pressure is bigger, that level of fluid will drop, and the other level will go up if it's bigger because you have that pressure differential. So if we take this pressure right here and make it 0, we create a special case for the manometer, and it looks like this. We have some fluid. We have a pressure that's pushing down on it, and it causes this fluid to go up into this column. All right, and it goes up to a certain height. And the pressure inside the tube is equal to 0. All right, so this is the same setup as what we have here, except I'm just letting this pressure equal 0. So basically I'm just capping this off, and I'm sucking everything out of that tube so that there's a vacuum inside of there. And so this theoretical limit for the straw occurs when you have created a perfect vacuum at the top of the straw. And then you can't create a vacuum. You can't create less than a vacuum. So that's the theoretical limit. And then if you calculate then the height of this column, H, that will give you the atmospheric pressure. So remember, atmospheric pressure, or this pressure that we want to measure right here, is equal to rho GH plus this pressure right here. This pressure is 0. And then you can solve this for H divided by rho times G. So this is 1 times 10 to the 5th newtons per square meter. The density of water, y'all remember the density of water in grams per cubic centimeter? What's the density of water? It's a real easy number. it's equal to 1. In kilograms per cubic meter, the SI unit, it's 1,000. It's 1,000 kilograms per cubic meter times G, which is 10 meters per second squared. So that's 1 times 10 to the 5th over 1 times 10 to the 4th, so that's 10 meters. This is, do y'all know what this is called, by the way, this device? This is sort of an aside, but it's not entirely an aside. What is this device? It's a manometer when we set that pressure equal to 0, when we have a vacuum on the one side of the manometer. This is called a barometer, and it's how we measure atmospheric pressure. All right, so it's exactly like this. And if we had water inside of this barometer, it would need to have a 10-meter column, a column about 30 meters high. But we don't usually use water. What do we use in these? We use mercury. Likewise, when you're measuring blood pressure, you use mercury. Do you know why we use mercury for those things? Because it's a toxic metal, right? If it gets out and gets into your, makes contact with your skin or if you ingest it, it's bad for you. Huh? Yeah, but you're not supposed to hold it in your hand. Like, that's very bad. Why do we use mercury for these? It's what? Right. Cal said that it doesn't require a solid column. And you said, well, why is that? It's heavier, right. It's more dense. So that density rho is a lot bigger than it is for water. So you only need, whereas with water you need a 10-meter column, with mercury you only need 760 millimeters, like that high. So that's a lot easier, right, even though it's a toxic metal. All right. So that was pressures, manometers, and now we're going to move on to Archimedes Principle, which measures buoyant forces, and then also we'll do Bernoulli's equation and the flow of fluids and how we use that for Venturi's and entrainment of liquids. I'm going to show you a video right quick. This is from Bill Nye the Science Guy. Y'all ever seen him? Yeah, he's talking about buoyancy. It's kind of fun. I think it's he gives a pretty good explanation. All right. So Archimedes' principle describes the buoyant force. And it says that an object in a fluid that is a fluid is either a liquid or a gas. A fluid is anything that does what? Anything that does what? Anything that flows. A fluid is a liquid or a gas, anything that flows. It says an object in a fluid will experience an upward buoyant force equal to the weight of the displaced fluid. All right, so our buoyant force, it's called BF in your book, but I'm going to call it F with a subscript B. All right, so because it is a force, and it's just a particular type of force, the buoyant force, and it's equal to the force weight of the fluid that's displaced. All right, so when he put the boat in the tank of water, it displaced a certain amount of fluid, which he put in those two large beakers, and then he showed that the mass of that fluid was equal to the mass of what? Of the boat, right? So the mass of the fluid was equal to the mass of the boat. That means that the weight of the displaced fluid, was equal to the weight of the boat, which in this case was the buoyant force. So if I consider if an object floats, like the boat, the buoyant force is equal to the weight of the object. So if I have a boat, for example, and it's in water or whatever, it has a certain weight, the actual weight of the boat, and then it also has a buoyant force that is pushing back up onto it. And since the boat isn't moving, it's neither moving up nor down, accelerating in either direction, we know that these two forces, the buoyant force, has to equal the weight of the boat. So the buoyant force is equal to the weight of the displaced fluid, and when an object floats, the buoyant force is also equal to the weight of the object. Let's do an example. I have a cork that has a density of 0.24 grams per cubic centimeter, and I go on from here. All right. I have a cork has a density of 0.24 grams per cubic centimeter. And I want to know what is the I'm floating this cork in water. So this is my cork right here. And I'm floating this cork in water. And I want to know what fraction of that cork is actually displaced, or what fraction of it is submerged. What fraction of the cork is submerged in water? All right, I can draw my force diagrams. I know that I have a buoyant force pushing up, and I have a weight that's pushing down. And I know that those two have to be equal, that the buoyant force is equal to the weight. But then I also know from Archimedes' principle that the buoyant force is equal to the weight of the displaced fluid. All right, so this cork is displacing a certain amount of fluid that's equal to its weight, because the buoyant force is equal to the weight of the object, and the buoyant force is also equal to the weight of the displaced fluid. So it should follow then that the weight of the cork is equal to the weight of the displaced fluid. Let me just write that in words. So the weight of the cork, FW then, has to equal the weight of the displaced fluid. The weight of the cork that's FW, equals the weight of the displaced fluid. That's going to be FW of the fluid. All right. I can find the weight of the fluid because I'm displacing a certain amount of fluid. All right, I'm going to call this the volume submerged, the volume of the cork that's below the water line. And then I know then that the amount of fluid that's displaced, the mass of the fluid that's displaced, is equal to the density of the fluid times the volume of the fluid that's displaced. And so this is going to be the density of the fluid times the volume of the cork that is submerged. This comes from the definition of density. Remember, rho is m over v, and so the mass then is just the density times the volume of the fluid. And then I know the volume of the density of the fluid. This is just water. But this volume of, the density of the fluid is water, so it's 1 gram per cubic centimeter. And then the volume of the fluid is just the amount that's submerged on the cork. So if this cork is submerged halfway, then that volume that's submerged is equal to the volume of the fluid that it displaces. Anytime you put something in water or in a fluid, a liquid or a gas, it displaces a certain amount of that liquid, right? And that's going to equal my submerged volume of the object. You tracking with me on this? Yeah? Hmm? We'll work another example. We'll see. I'm going to show you a video too. So let me finish up here. So my mass of the fluid is this. And so that's going to come into play over here because the weight of the fluid is equal to the mass of the fluid, or excuse me, sorry. This is my force weight. The weight of the fluid is equal to the mass of the fluid times G. The weight over here is the mass of the cork times G. And then I can plug this in for the mass of the fluid. And so that's the density of the fluid times the volume that's submerged times G. And then I cancel out my G's. And I want to know what is the submerged volume. So I'm going to divide both sides here by the density of the fluid. So it's going to cancel out there. And then I get an expression for the submerged volume. All right, which is what I wanted to know in the first place. What is the submerged volume? Is mass of the cork over the density of the fluid. All right? I don't know the mass of the cork, but I know its density. So I can say then that the mass of the cork is equal to the density of the cork times the volume of the cork. And I'll plug that in here. And I'll get that the submerged volume is equal to the density of the cork over the density of water, that's my fluid, times the volume of the cork. And so if I want to know the fraction that's submerged, I just take the density of the cork divided by the density of water. So what fraction of my cork is going to be submerged? What percentage is going to be submerged? My density of the cork is 0.24. What's the density of water? It's 1, right? And so 0.24 over 1 is just 0.24. Yeah. Oh, it's given, no problem. Yeah. So I can find the amount that's going to be submerged. It's going to be the density of the object divided by the density of the fluid. That's a nice little tool to have because that means that you put any object in the water, you can figure out its density really quickly just by looking at how much of it floats. Right, so if you float in the pool and only half of your body is submerged, what's your density? What is it? It's 0.5, right. So if half your body is submerged, that means that your density is 1/2 of that of water. Or if 3/4 of your body is submerged, that means that you're more dense. It's going to be like 0.75. Right, so this is a nice little tool to figure out the density of irregular bodies. And that's Archimedes, when he first came up with this Archimedes Principle. Remember the story, he's in the tub, right? And he jumped up, he's naked, ran through the streets. He said, Eureka. I don't know if that's true, but that's the story they always tell because he had realized that he had a way where he could determine what was gold and what was not gold because he could use this method in order to determine the density of unknown substances or the density of complicated substances. I'll work through another problem soon. But this is a real nice application because we often want to know the density of objects that are irregular, like the human body. Yeah, Kyle? How do we know what fraction is? Yeah, 24% will be submerged in water. If it was more dense than water, or if it was more dense than, say, 0.24, say it was, the density was 0.5, or let's say that the density was 0.7, then that would mean 70% of it. Right, if it goes over the density of water, then the whole thing's going to sink. Yeah, Tarion, right? Yeah. Yeah, the density of water, it's on your equation sheet, actually. Yeah, it's equal to 1 gram per cubic centimeter. So it's a nice little number to just have in your head. The density of water is 1. But it is on the equation sheet. All right. I know this seems complex now. Like in this problem, there were a lot of little steps that you had to take, but I'll work through some simpler problems where you'll see that the steps aren't quite so complicated. Yeah. Oh, so if I want to, the volume of the cork comes into play because I want to know what fraction of the cork is submerged. So I divide both sides by volume of the cork. So the submerged volume divided by the volume of the cork is equal to the density of the cork divided by the density of water. So that's 0.24 over 1. So this is the percentage that are the fraction of the volume that is submerged. So if this was completely submerged, the volume that's submerged would equal the volume of the cork. And then this would equal 1. Is that clear? Let me work another example that's a little simpler, just finding the buoyant force of something, and then we'll come back and I'll show you a neat little application for this. What's that? Just forget all this for right now. Yeah, we're going to work a simpler problem. I know there are lots of steps here, but really the only things that we're playing here are the buoyancy, which is equal to the weight of the displaced fluid, and then we're playing around with the density of fluids, the density of objects. That rho is equal to mv. All right, let me show you a simpler problem, okay? Let's just say that I have a boat. All right, I have a boat. It has a volume. It's a big boat. It has a volume of 1,000 cubic meters. So that would be like a 10 by 10 by 10 meter boat, a 30 by 30 by 30 foot boat, a cubical boat. Anyway, you get about 1,000 cubic meters. It has a mass equal to 1,000 kilograms. Right? It's made out of steel or whatever. It's a pretty heavy boat. I want to know how much this boat can carry. How much mass can this boat carry? All right, so I have this boat. Looks like an anvil. I'll put a sail on it. There you go. I have a boat. It has a certain mass, and it has a certain volume. I want to know how much this boat can carry. I have two forces that are at play. I have the force weight, and then I have the buoyant force. And I know if this boat is to float, that the buoyant force has to equal the weight. All right? My buoyant force is equal to the weight of the displaced fluid. So the buoyant force is equal to the mass of the displaced fluid times gravity. And then that's equal to the mass of the boat times gravity. All right? I want to know what that mass is. Now, my mass of my displaced fluid here, I know that density is equal to mass over volume. So then mass is equal to density times volume. I just multiply both sides by volume. And so I can replace this mass of the displaced fluid with the density of the fluid times the volume of the displaced fluid. All right. In this case, I'm going to assume that my entire boat is submerged. So it's submerged right up to the, what's that called, the gunnel, right up to the top of the boat. All right. So just before water begins seeping over into the edges. So that means that all of my fluid is being displaced. Like the entire volume of the boat is displacing the same amount of water. Times G, and then this is equal to the mass of the boat times G. I can get rid of these G's. All right, and I want to know how much mass this boat can carry. That includes this whole mass. So this mass, the mass of the boat, includes not only the mass of the boat, but also what's inside of the boat. And so that mass of the boat, which includes its cargo, is equal to the density of the fluid times the volume that's displaced. All right. The density of water is equal to 1 gram per cubic centimeter, but we need to convert this to kilograms per cubic meter. And for the test, you'll be using both of these densities, and I'll provide both of them to you. That I'll provide it in grams per cubic centimeter, but then I'll also provide it in kilograms per cubic meter. So it's 1,000 kilograms per cubic meter. You'll know when to use that just by looking at the units. And I know that here because these units are in kilograms and cubic meters, and that should be a signal to you that you need to use the same units for the density. All right, so the density of the fluid is 1,000 kilograms per cubic meter. And then the volume of the displaced fluid is equal to the volume of the boat, so that's 1,000 cubic meters. So that's 1 with 6 zeros. That's 1,000,000 kilograms. So in this boat that has a volume of 1,000 cubic meters, it can displace up to 1,000,000 kilograms of water. So what's the maximum cargo that this boat can carry? It's going to be 1,000,000 minus what? Minus 1,000, right. So this boat will be able to carry, what's that, 1,999,000. 999,000. Right? So 1,000,000 minus 1,000 is the amount of mass the boat can carry. So 1,000,000 minus 1,000 kilograms, which is the mass of the boat, which is 999. So the boat can carry 999,000 kilograms. That's a little more straightforward? No? Or yeah? No? We'll work through some more examples. I want to show you an application now, though, and then we'll work through some examples. And then there are also some homework questions regarding this. So as I said, this is a nice thing because it allows us to measure the density of irregular objects like the human body. So you commonly use this. You'll put a person into a water tank and measure their buoyant force, and then you can determine their density very accurately. So this is a little clip about this lady. She goes, all right. Basically, all that is it's just a scale inside of a big tank of water. And so it puts you inside the tank of water, and it measures your new mass. Is it going to be more or less than your actual mass? If you're inside of a tank of water and you measure your mass, more or less? Okay, I'll show you. It'll be less than your actual mass. But let's work through a simpler problem first. It'll be similar. Let's say that I'm in a tank of water, much like this lady was in a tank of water. All right, and I'm fully submerged. All right, I'm underneath the water and I'm fully submerged. And I want to know let's see, let's say that I'm on a scale. I'm attached to a scale that's underneath the water, like that, and it measures a force. It measures a force up here that is my weight. And it tells me that this mass, or this force, weight, that's measured is equal to, say, I don't know, 500 newtons. All right? But I know that my actual mass is more than that. It's 1,000 newtons. All right? So I know that when I go into the tank that I weigh less than I actually do because I have this buoyant force that's pulling up on me. So if I look at this and I label the force vectors, I have 3 force vectors that are at play. I have first the weight of the person. That's his actual weight, his actual mass times the acceleration due to gravity. Then I also have the buoyant force that's acting on him. And then what's the other force that I have acting on him? I have the weight of the person pulling down. I have the buoyant force that's pulling up. And then I have one more force that's pulling up. What is that force? No, not the gravitational force. That's what's pulling down. All right. What is holding him up in the water? Otherwise, he's just going to sink to the bottom. What's holding him up in the water? The pulley thing, right. So the scale is pulling up. And I know the force it is pulling up with. What is that force? It's 500 newtons, right? Because that's what it's reading on the scale. This is just like what the lady is doing in the clip. They know her actual mass, and they know the mass that the scale is reporting in the tank. And so this is going to be, I'm going to call it FW measured. It's equal to 500 newtons. All right. I know this. This is equal to 1,000 newtons. So I can find the buoyant force. The buoyant force plus FW measured minus FW is equal to 0. Remember, that's Newton's second law. The sum of the forces is equal to the mass times acceleration. In this case, my acceleration is 0. And so the sum of the forces have to all add up to equal 0. All right, so you can probably tell just from looking at the numbers that if I have 1,000 newtons here and 500 newtons here, then this force has to be what to equal it all out? 500, right. So my buoyant force is equal to 500 newtons. That's a pretty simple thing to get because I just need to take the difference between my actual weight and the weight that's reported on the scale, the so-called apparent weight, and I get the buoyant force. Now, I can come over here because I really want to know what is the density of the body. And then they can convert that into pounds of lean mass, pounds of fat, and pounds of muscle and bone, and get those percentages that she was showing. So I know that my buoyant force from Archimedes Principle is equal to the density of the fluid times the displaced volume, that's the volume of the object in this case, times gravity. All right. This equation is on your equation sheet. This is Archimedes' principle, that the buoyant force is equal to the weight of the displaced fluid. The weight of the displaced fluid is the mass of the fluid that's displaced times the acceleration due to gravity. That's the density of the fluid times the volume. That gives me the mass times the acceleration due to gravity gives me the weight. All right, so the buoyant force is equal to that. I know the buoyant force is equal to 500 newtons in this case because of what we did over here. I know that the density of water is 1,000 kilograms per cubic meter. I don't know the volume of the object, but I know the acceleration due to gravity is 10 meters per second squared. So then I can find the volume of the object. I divide both sides by 1,000 times 10. That's 10,000, 10,000. And so the volume of the object is equal to 5 over 100, 0.05 cubic meters. I'm just making these numbers up. That's not a real reasonable value. But the volume of my object, this person in this case, is 0.05 cubic meters. All right? Are y'all with me on this? Are there questions at this point? Things to clarify? Archimedes' principle, the buoyant force is equal to the weight of the displaced fluid. That's what's on the right-hand side there. On the left-hand side is just Newton's second law, that we can sum up those forces, and they have to equal to 0. With me so far? Yeah, sort of. Maybe, okay. I'll take a maybe for now. So the volume of the object is there, but really I want to know the what of the body. Yeah, Terry on? Hold on, let me come back. I didn't have to find the FB. Yeah, on the previous, you said that on the previous problem that we didn't have to find FB. Right, I'm sort of working it a little bit differently here. In the previous problem, I made some substitutions, and I think that might have confused some of y'all. So I'm trying to do it in a simpler way. Is that okay? Yeah, is this a little simpler? Okay. All right, so my volume of the object is 0.05 cubic meters, but really I want to know what is the density of the object. All right, so density is just mass over volume, but mass is really easy to get, right? You just pop somebody on a scale and you get their mass. So I want to know the density And so the density is mass over volume. That's going to be some mass over 0.05 cubic meters. As I said, these numbers don't make much sense because I'm just making them up. But 0.05 cubic meters. And then my mass is 100 kilograms. That comes from up here because I know that FW is equal to mg, which is equal to 1,000 newtons. So my actual mass of my person is 1,000 newtons over 10 meters per second squared, and that's equal to 100 kilograms. All right, so my mass is 100 kilograms over 0.05. I get 2,000 kilograms per cubic meter. That's the density of the person. That's a very dense person, twice the density of water. Sam? So, after I found the volume of the object? Okay. All right. So I want to know the density of the person. When you do these measurements, you want to know their density, right? That's really the important number because you can convert that into pounds of muscle mass, pounds of fat mass, and all that stuff. I want to know the density of the muscle, or the density of the person. So I need to take the mass of the person and divide it by the volume. Now I found the volume here. That's what all this jazz was from. With Archimedes Principle, finding the volume of the person that's submerged in water. So I need to also know the mass of the person. Now, in a lab setting or in your, I don't know, in your measurement room or whatever, you would just put the person on a scale, measure their mass, and have it. But here we don't have their mass. We have their actual weight in newtons. So we need to convert that weight into kilograms. Remember, there's a difference between a force and a mass. So that's what I did up here. I know that his weight is 1,000 newtons. And so to convert that into mass, I just divide by the acceleration due to gravity. And then that gives me the mass, which is 100 kilograms. So now I have everything I need to find the density. 100 kilograms over 0.05, which is 2,000. Does that help me clear it up a little, Sam? Yeah? Yeah, carry on. Find the mass, we divided it. Let me look. On the previous problem, oh, on the previous, with the boat, you mean? Yeah. With the boat, though, we were, I gave you the mass of the boat, and then I wanted to know what additional mass you could put into the boat. So I wanted to know the total mass of the boat with the cargo, and we found that the total mass of the boat with the cargo was 1,000,000, but the mass of the boat itself was 1,000 kilograms. So that's why I subtracted it out, so I could find what is just the mass of the cargo. Yeah? Okay. There are some more homework questions with this. You will see it on the quiz on Tuesday, all right? Like you will have to calculate the density of an object or the volume of a displaced object or something along those lines using this Archimedes principle. Okay, could y'all do that? Right. Let me step through it again. So on the left-hand side, I find the buoyant force. That's just applying Newton's second law. I know the force is pulling up on them. I know the force is pulling down on them. So I can figure that out because I have the buoyant force, the measured force, and then its actual weight. So my buoyant force has to equal 500 newtons, right? Mm-hmm. I mean, it's not always going to be those numbers, but yeah. The buoyant force is always going to be the difference between the actual weight and the apparent weight. That's your measured weight. That's what you appear to be when you're submerged in water. Okay? Is that clear, this part? This is just applying Newton's second law, that if I have to have a balanced set of forces on either side, so the forces pulling down have to equal the forces pulling up. Right. The actual weight minus the measured weight. In your book, they call that apparent mass and apparent weight, right? And actual mass or actual weight. So this is my buoyant force. Once I get my buoyant force, I can apply Archimedes Principle in order to find the volume of the object. And that's what I've done here. So this is the second step. You find the volume of the object. And then the third step is to find the density of the object. Because once I have the volume, it's easy to get the mass. I can find the actual density. So this person, I said, has a density about twice that of water. Okay? This is a really nice technique for determining density of irregularly shaped objects. This is really the only technique that you can use to place them in a big water bath, basically. All right? You could build one of these your own, I think. I mean, you just need a scale and a big tank of water. That's not that hard, right? But these are made very accurately when they do these hydrostatic weighings. Okay? All right. I'm around. Like, if y'all need help with this, I can always sit down with you, too, and help you. Kyle? Yeah, like on the bottom of that tank, there's a platform, and she hangs onto that platform and measures. So when she's fully submerged, it measures what is her mass. She's sitting on top of it because she doesn't float, right? She was pretty dense. And when you let all the air out of your lungs, that's why you let all the air out of your lungs, so that you're not affected by the buoyancy of your lungs. You ever been in the swimming pool? And if you want to sink to the bottom, what do? Just blow out all the air, and then you'll sink to the bottom. So that's why she had to blow out all the air. But it's just a scale inside of a tank of water. It's a fancy scale, no doubt, right? But it's still just a scale. All right. Y'all have one of these? Do you have one in athletic training? No? Okay. I think they're kind of cool, actually. Okay. In your book, we're going to skip the section on flow, and we're going to go right to Bernoulli's principle. Bernoulli's principle, we're not going to treat mathematically either. I'm just going to treat it as a conceptual thing, but it's still really neat. It has a lot of applications. Bernoulli's principle. It says that when the speed of a fluid is high, the pressure is low. And when the speed of a fluid is low, the pressure is high. Your book gives the actual equation for this, but don't sweat that. We're not going to deal with the mathematics of Bernoulli's principle. But when a fluid goes very fast, its pressure drops. And when a fluid goes really slow, its pressure increases. Now, when we couple this with something else called the continuity equation, let me just write this. So if V goes up, pressure goes down. If V goes down, pressure goes up. That's Bernoulli's principle in short. If the velocity increases, the pressure goes down. If the velocity decreases, the pressure goes up. This has an application in aircraft wings. They build these aircraft wings to look like this in short. This is very simple description, but you have air that comes over these wings, and then the air splits here, and the air on this side has to travel a further distance than the air on the bottom. So on this side, we get a high velocity flow, because otherwise, if it doesn't travel at a higher speed, it'll create a vacuum on top of the wing, and that doesn't happen very easily. So I get high velocity flow of air over the top of the wing, and as a result, I get a lower velocity flow of air across the bottom of the wing. And if I have a low velocity, that means that I have a high pressure. And if I have a high velocity, that means that I have a low pressure. All right? So that causes this pressure differential and causes what on the wing? To be pushed what? Up or down? It causes it to push up because I have high pressure on the bottom and a low pressure on the top, and that causes lift. So Bernoulli's principle is the idea behind the lift in airplane wings, aircraft wings, but it also has a bunch of applications because it allows for the entrainment of fluids. And entrainment is the pulling of one fluid into the flow of another. Of another. Any respiratory techs in here? I don't think there are. I don't think y'all have respiratory techs anymore coming through. But respiratory technicians will use this a lot because they'll want to, as patients are inhaling air or oxygen through a tube, they might want to entrain some fluid into that, maybe a medicine or maybe just water to provide more humidity in their lungs. All right, so entrainment is the pulling of one fluid into the flow of another. This has a lot of examples. For example, a Bunsen burner works by this method. You have natural gas that comes into a device that looks something like this. So you have a tube that comes into the bottom of this with natural gas that comes into this tube, and it's sucked up into this column. So this natural gas, let's see, I'll draw it as a blue. Natural gas comes up into this column. All right, this is high velocity gas. That means it has low pressure. And if it has low pressure, it has a little vent on the side here of the Bunsen burner. It's going to have a low pressure on the inside, a high pressure on the outside. So what's going to be the result? I'll suck in air from the outside. All right, so outside you'll have air. This is a high pressure, relatively, and so it gets sucked into the Bunsen burner. And of course, you need air or oxygen for combustion, so it allows you to have very hot burning of this natural gas because of the air that it sucks into it. You have a perfume atomizer. I don't think people really use these much anymore, but really your little squirt bottle is the same. But I have my perfume. This is an atomizer. This is a Bunsen burner. I have perfume that has a tube that goes down into it, and then I have a bulb here that blows air over this open tube. So I blow air through this open tube with a high velocity. That means that it has a low pressure. All right, and so in a similar way, because it has this low pressure, in a similar way to this, it's going to suck up some of this perfume and suck it into that stream of air. So when you squeeze the little bulb, you know what I'm talking about? Y'all probably don't have these. Do y'all have these things? You know what I'm talking about? Y'all have those? No. Yeah, you do? Yeah? Okay. Well, maybe they still do sell them. It sucks up because of the Bernoulli principle. High velocity gives me low pressure. It's going to suck up some of that perfume. Not very much, just really just a few particles, which is all you need. It'll suck up some of these particles of perfume, and they'll get entrained into the flow of the air. There's an Aspirator Suction Cup. There's a picture of this in your book, I'm pretty sure. Suction pump. This is a really easy way to suck things out of stuff. You really just hook it up to a water faucet. I think it's kind of neat. You have a device that looks something like this, and water comes in here and travels through here. Now it gets smaller, so it requires it gets a higher velocity inside this tube, and then you have another tube here that comes into the side where you have air coming in here. So you have this high velocity water, and it causes a low pressure and will suck in air from the side. Let me show you a picture on the internet. This is from the wiki page. Oh, that's my mail. Sorry. Okay, well the internet's kind of slow. I'll pull it up later and show it to you. But this is called an aspirator suction pump, and it just causes you to pull in air. One more thing, and then we'll work through some problems. I know we're almost done, but I want to show you the equation of continuity, and then we'll come back to this on Tuesday. And if you all have questions about the Archimedes Principle or Bernoulli or equation of continuity, we can readdress those on Tuesday. So we'll have some time to review before the quiz, or if you want to come see me sometime between now and then. Now, the equation of continuity is closely related to Bernoulli's principle, and it's pretty simple, actually. It just says that if you decrease the area through which a fluid is flowing, that you're going to increase the velocity. Continuity. There we go. So it says that, let's say you have a pipe like this. It's called a Venturi tube, right? And I have a certain amount of fluid that's flowing through here at a certain velocity. And then it goes into this part, and it has a new velocity. I can describe the area of these. This is the area. I'll call it A2. And then this has an area, A1. What's going to happen when the fluid, water or whatever, gas, what's going to happen when it travels from the big tube at a certain velocity to a smaller tube at a certain velocity? What's going to happen to its speed? Is it going to speed up, slow down, or travel at the same speed? It's going to do what? No. What's it going to happen? I have a whole big old mass of water, and it's coming through a pipe, and then it goes to a smaller pipe. Now, I can't lose that water, right? It's not going to go anywhere. What's it going to do? It's going to go faster because I still have to squeeze that big old amount of water through that little bitty pipe, okay? And so it's going to speed up because when I go from a big section of pipe to the lower section of pipe, it speeds up. What's a good example of that you experience at home or whatever? Hose, yeah. How do you make it come out faster? You put your thumb over it. You're decreasing the cross-sectional area of the hose, or you can sort of squeeze the hose down to make it smaller, and then it comes out faster. But if it comes out faster, is the pressure more or less? No, the pressure decreases. I know it feels like it's a higher pressure, but it's actually lower pressure because Bernoulli's principle, right? If V goes up, pressure goes down. All right, so the equation of continuity just says that the product of the area and the speed has to remain constant. So it says that A1 V1, this is V1 right here, has to equal A2 V2. All right? So for example, if A2 goes down, as it has here, V2 goes up. If the area gets smaller, the velocity has to increase. And that goes back to that aspirator suction cup. Like here, when I have the water that comes through this little tube right here, it has to speed up, which creates that high velocity and hence low pressure. Let's see if my website came up yet. Doesn't look like it. All right, I'll bring a picture next time of the aspirator suction cup. Let me just do a quick example, and this will be the last one. So as I said, if you have trouble, if you're still having trouble with the Archimedes Principle, please come see me. You'll see it on the test for sure, so please come see me. And also, just be aware that some of the homework questions are like the ones that I've worked here, where they have a multiple steps. But on the test, your problems won't have that many steps. There'll be 1 or 2 steps that you'll have to take, but they'll be sort of subsets of those problems. Is that clear what I mean by that? Because you can't work through one of those problems on a 15-question test in half an hour. Let's just do a quick example. I think this is kind of intuitive, but maybe it's not. Let's say that I have a pipe. It's 2 centimeters in radius, and it goes to 1 centimeter in radius, like this. A Venturi tube, they're called. The radius, actually, I'll give you the area. The area is, say, 2 centimeters squared. I'll call this A1. Now let's say that V1 is equal to 10 centimeters per second. And then V2, the flow of the water over here, I want to know. And my new cross-sectional area, A2, is 1 square centimeter. I just say A1 V1 equals A2 V2. That is 2 times 10 equals 1 times V2. So V2 is equal to 20 centimeters per second. If the area decreases by half, the velocity or the speed of the fluid has to increase by that same amount. So if the area drops by a factor of 2, the velocity goes up by a factor of 2. All right? Any questions? Yeah. All right, so the quiz will be on Tuesday. It'll be just like before, half an hour at the end of class. We will have time to review during class. So if you have questions, then please bring them or come see me before. If you're really struggling with this, I think coming to see me is probably the biggest help to you. So I know you all have busy schedules, but my schedule's pretty open. I'll be around all day tomorrow afternoon. Those 2 chapters, fluids, and then the previous chapter was on calorimetry and heat and temperature and all that business. Okay? Sam? Oh, really? The screencast? Yeah, I'll look and see. I'm sorry, I'll take a look at that. Okay. It might be that it doesn't, it might have had trouble with the recording, but I'll see what I can fix. All right, you guys, have a good day, okay? I'll see you on Tuesday. Y'all have a good weekend. If you want to come see me, okay, for extra help, please do. Bye. Oh, I'm going to the science fair. If I'm not there, though, you can. Oh, thanks. It's Deshaun, right?